Hello, this is Miraj Patel, and today we're going to be talking about empirical formulas, and we're going to be talking about percent composition. And before I begin, I'd like to thank Miss Harper again for teaching me all the knowledge and providing me with the PowerPoint so I can be sharing it with you. And so pretty much Unit 7 is pretty short. All it is just chemical composition of elements and compounds. And so first we have percent composition we're going to learn about, and then we're going to be applying it to empirical formulas, which we'll talk about in this video also. And so here, we have you know how shirts on the tag tells you the percent components of a shirt, and it's important because they affect how warm it is, whether it'll need to be ironed, and how it should be cleaned. And same thing in chemistry, percent composition is important because it tells you how much of the compound is made out of which element, and it also determines properties because each element has different, or each molecule has different percent compositions. And so we're going to be talking about how to calculate it. So percent composition is, by mass at least here, is calculated by dividing the mass of the element by the total mass of the whole compound times 100 to get a percent. And so this diagram shows us the percent composition of potassium chromate, which is C₂CrO4. And so pretty much we have the whole molar mass of this whole thing, which is gotten by multiplying the atomic mass of all the different elements times the number of each of the atoms of each element. So we have 2 potassium, and then we have 1 chromium and 4 oxygen, so we'd multiply them by their corresponding atomic mass and the number of the elements with that atomic mass, and then we just add them all up and we would get this. And out of the whole mass, so 194.2, it tells us that there's 26.8% chromium, 32.9% oxygen, and 40.3% potassium. And then same thing here, we have potassium dichromate. And so pretty much notice how the percent changed because there's more chromium percentage than in potassium chromate because we added 2 chromate, or a second one here. And there's higher percent oxygen because there's 7 oxygen now instead of 4. And then potassium's percentage decreased because we added more of the other elements but no more potassium. And so here is one problem. So calculating percent composition from mass data. And so here we have 13.6 gram sample of a compound containing only magnesium and oxygen is decomposed, and 5.4 grams of oxygen is obtained. So what is the percent composition of this compound? So whenever it says what is the percent composition, we want to find the percentage of each of the elements in the compound. And so here we have to determine what we have. So we have 13.6 gram sample, so that's the total mass. Then we have 5.4 grams of oxygen. So and it's also asking percent composition. And so the formula is mass of an element divided by the total mass of the whole compound times 100. And so here percent oxygen would be the oxygen's mass of 5.4 grams divided by the total, which is 13.6 grams, and we would get, and then we multiply by 100 and get 39.7%. And then to find the percent composition of magnesium, you might be wondering, they didn't give us the grams of magnesium, but we can figure it out because this compound only has 2 elements and it tells us 1, so we can just solve the weight of the other element by just subtracting 13.6 minus 5.4, and we would get 8.2. So 8.2 grams is magnesium, because if it's not oxygen, it has to be magnesium. Then we divide it again by the total mass and multiply by 100 and get 60.3 grams, or percent, of this whole compound. And so if you want to know a quick way to do this, if we have only two elements, you can just find the percent composition of one of them and then figure out the percent composition of the other one by subtracting the percent composition of the first element from 100. So if we subtracted 39.7 from 100, we would get this, because there's only two elements. So if we know the percent of one, everything else has to be the other element. And so that's a quick way. And you can do this with compounds with three. If you figure out the percent composition of two of them, you can just subtract it from 100 and do the same exact thing. And so here's calculating percent composition from a formula. So this one, it doesn't tell you how much grams of carbon or hydrogen there are, it just tells you the formula. So propane, the fuel commonly used in gas grills, is one of the compounds obtained from petroleum. Calculate the percent composition of propane. So again, the formula is mass of the element divided by total mass times 100. So we have C₂H₄, and so we want the percent composition, and so we have to first figure out the total by multiplying the number of carbons, so there will be 3 carbons, times the atomic mass of carbon, and then adding it with the number of hydrogens times its times the atomic mass of hydrogen, and we would add these two up and we get 44.1, and then we can find the percent composition of carbon by finding out how many carbon there are and multiplying 3 times carbon's atomic mass, because there's 3 carbons, so it'd be 36.3, and if you have calculated the total, you should just leave your work, and this would be carbon, because 12.01, which is atomic mass of carbon, times 3, you can just literally put this in on the top and divide by 44.11, and then multiply by 100, and you get the percent of 81.68, and then finding percent of hydrogen is this part of the formula, so 8 times 1.01, which is hydrogen's atomic mass, and the number of hydrogen, and then we divide by the total, which is 44.11, and multiply by 100, and we get 18.32. And again, you could have just got the percentage of carbon and subtract this from 100, and you would have got the same answer for a percent composition of hydrogen. And so here's the last problem before we move on to our quiz. So calculate the percent nitrogen in these common fertilizers. So we have NH3 and then NH4NO3. And so here I'm nice and I give you the grams per mole, or atomic mass, of this whole molecule. And if you didn't know how to do this, you just go to the periodic table and we just count the number of nitrogens, multiply nitrogen's atomic mass, and add it with the atomic mass of hydrogen times 3, because there's 3 hydrogens, and we would get 17.04. So here, the percent nitrogen in the first one, NH3, would be 14.01 times 1, which is the same thing as 14.01, and we divide it by the total, which is right here, the molar mass, and then multiply by 100, and we would get 82.22%. And then we have the last chemical here, and so again, I'm nice and I give you the whole molar mass of this whole compound, and again, it's the same thing. You just count the number of each element and multiply the element by its corresponding atomic mass. And so here we have 2 nitrogen this time, so it's 14.01 times 2, which is 28.02 if you punch in your calculator, and we divide by this total right here and multiply by 100, and we get a mass of 35%. And so here's a quick quiz. So the percent composition of a compound is found by dividing the mass of each element by the A, moles of each element, B, percent of each element, C, the total mass of the compound, or D, the total number of elements. So when we're finding percent composition, we're looking at mass. So we find mass of each element, and then we divide it by the whole compound's mass, and that's how we get a percentage. Because if you remember, percentage is the part of the whole that the element takes up. So at least in this scenario, when we're talking about percent composition, we're trying to find out how much of this compound is made of oxygen or carbon. So we divide the mass of each element by the total mass of the compound, and that's how we get a percent of the whole compound. Then we have problem number 2. So calculate the percent mass of carbon in C₂H₄N2. And so if you take out your calculators and go to your periodic tables, so first we have to calculate the total, so we can divide the mass of the carbons from the total. And so you have the periodic table, so we first have to count the number of each element and multiply them by their corresponding atomic masses and then add them up. So we have 5 carbons. So we have, and carbon has atomic mass of 12.01, sorry. So 5 times 12.01, and then we add that with a 1.01 times 14 because hydrogen's atomic mass is 1.01. So plus 14 times 1.01, and then we add that with nitrogen times its the 2 nitrogens, so 2 times nitrogen's atomic mass, which is 14.01. So plus 2 times 14.01. Then we add that up and we get 102.21. So if you want to write it down, so that's the total mass of this whole compound. And then we have to find the mass of carbon, just the carbon. So we have 5 carbons, so 5 times 12.01 is the mass of all the carbons, and we divide it by 102.21 and multiply this by 100, and the correct answer is B. And this isn't really done well, but the correct answer is B, because if we divide 60.05, which is the mass of the carbon, divided by 102.21, you would get about 58%. And moving on, now we're going to be talking about empirical formulas, and we'll just talk about what exactly is an empirical formula if you haven't heard about it, so don't worry. And so here we have some common compounds in like science. And so here we have, first we have formaldehyde, which is C₂H₂O, and that's a toxic preservative that was used to preserve frogs, but now it's replaced by some other chemical. And so if you ever dissect a frog, you would have smelled how like terrible these preservatives smell. And then we have acetic acid, which is vinegar. And so the formula is C₂H₄O2, and then we have glucose, which is C₃H12O6. I'm sure most of you know that if you've taken biology. And so the similar thing about all these is, notice how there's there's the same number of oxygen, and there's always twice the number of hydrogen. And so this is called an empirical formula. So pretty much it's the basic formula of all these. So notice how there's the same number of carbon and oxygen, and there's always twice the number of oxygen or carbon. So see how there's 6 carbon, oxygen also has 6, and 2 times 6 is the number of hydrogen. So these all have the same basic formula, or empirical formula. So empirical formulas are like the simplified version of these more complex formulas. And so these all share the same exact pattern. And so empirical formulas are the smallest whole number ratio of the atoms in a compound. So pretty much just like in math, when we're simplifying fractions, you want the greatest common factor of these numbers so we can simplify it down to a simpler compound. And so here are examples of empirical formulas, and these are some molecular formulas that have the empirical formulas above. So we have C₂H₂. So both these, the GCF or Grace common factor is 6. So if we divide both these by 6, we would get 6 divided by 6 is 1, so we have 1 carbon. 12 divided by 6 is 2, so we get 2 hydrogen. That's how we get this empirical formula. And same thing with all these. So 2 and 2 are both divided by 2, so 2 divided by 2 is 1, 2 divided by 2 is 1, so we have 1 hydrogen, 1 oxygen. Same thing with lead, lead and oxygen here. We have 2 leads and 4 oxygens, both of them are divided by 2, so 2 divided by 2 is 1, 4 divided by 2 is 2. And then we have 6 carbon, 18 hydrogen, and 3 nitrogen. So the greatest common factor is 3 because 3 sort of limits the GCF. So 3 divided by 3 is 1, 18 divided by 3 is 6, and 6 divided by 3 is 2. So that's how we get empirical formulas from these complex formulas. And a good trick to know whether you're looking at empirical formulas or not is if you see an element that does not have a subscript, that means it has one element in this compound. So as soon as you see an element with no subscript, you know that's an empirical formula because 1 cannot be divisible by anything except 1. And dividing by 1 wouldn't do anything. So you notice how all of these, there's one element with at least subscript of 1. So if it has a subscript of 1, it's an empirical formula. Always an empirical formula. And so here we have two different compounds. We have acetylene, which is C₂H₂, is a gas used for welding torches. And then we have styrene, which is C₄H₄, which is used for making polystyrene or packing peanuts. And so here, these two compounds have the same empirical formula because the number of carbons and hydrogens is always the same. So the empirical formula is CH, but they have different molecular formulas. See how we multiplied this CH, we just gave 2 carbons and 2 hydrogens, but this one has 8 carbon, 8 hydrogen. So they have different molecular formulas, but the same empirical formula. And we're going to be talking about how to find empirical formulas from percent composition. And so here we have a cute little jingle here, so sing along. So percent to mass, mass to moles, divide by small, and times to whole. So percent to mass, mass to mole, divide by small, times to whole. Percent to mass, mass to mole, divided by small, times to whole. So if you just remember this little jingle, and this little jingle contains all the steps to get from percent composition to an empirical formula. So again, percent to mass, mass to mole, divide by small, times to whole. So here is our first problem. So what is the empirical formula of a compound that is analyzed and found to contain 25.9% nitrogen and 74.1% oxygen? So first step is we have to identify everything. So we have empirical formula, we need to find it, and we have 2%. And so the first step of our jingle is percent to mass, and so we literally just take off the percent sign and assume it's out of 100. So we just change the percent sign to a gram sign. So just change it to a G. So that's first step done right there. And then mass to moles. So we all know how to convert from grams to mole. You just divide by the atomic mass. So we divide nitrogen by nitrogen's atomic mass, which is 14.01, then oxygen by its atomic mass, which is 16. And so obviously we put grams on the bottom, so grams cancels out, and so we're just left with moles at the top. And then it says divide by small. So out of these two numbers, we pick the smaller one and divide both of them by the smaller number. So out of 4.63 and 1.85, 1.85 is obviously smaller, so we divide both numbers by 1.85, and we get 1 and 2.5, and then the last step is times to whole. So if one of these is a decimal, which there is in this case, we multiply by a number so that it becomes a whole number. So 2.5, if we have 1/2, we need to multiply by 2 to get a whole number. Or if it's a 0.3333 repeater, then we have to multiply by 3. So in your head, if you remember like decimals and their fractions, you just multiply by the, if you converted this like 0.5 to a fraction, you just multiply the reciprocal. So 0.5 is actually 1/2, so 1/2's reciprocal is 2. So if you have good math skills and know fractions and decimals, you would be it's easy to convert. So in this case, we multiply by 2 to get 5, and then we multiply 1 by 2 and get 2. So we have, at the very end, we have the empirical formula. So we have N2O5, or dinitrogen pentaoxide. And so just bringing back naming of covalent bonding. So here we have another problem. So we have 1,6-dimonohexane is used to make nylon. What is the empirical formula if it is 62.1% carbon, 13.8% hydrogen, and 24.1% nitrogen? So remember the first step, percent to mass. So obviously we're looking for empirical formula. So we go from percent to mass. So we just change the percent signs to g's, little g's, and then we do percent to mass, mass to moles. So we can divide them by the element that they're representing by their atomic mass. So carbon's is 14.01, or 12.01. Then hydrogen's is 1.01, and then nitrogen's is 14.01. I'm sorry, I keep getting carbon and nitrogen confused because they're so similar. There's only 2 off. And so we divide by the molar mass, and again we cancel out grams, and we're left with moles. So notice how grams is at the bottom of the fraction. We're left with moles, and then the next step is divide by small. So out of all of these, pick the smallest one and divide all of them by that. So 1.72 is the smallest, so we divide by all of them by that, and we get 3, 8, and 1. So 3 carbon, 8 hydrogen, 1 nitrogen, and then it says times to whole, but these are already whole numbers, so we don't have to do the last step. So we save this step. Woohoo! So the empirical formula is C₃H8N. And so here's a quick quiz to see what you learned. So question 1, an empirical formula shows the blank of atoms in a compound. A, the lowest common number, B, the highest whole number ratio, C, the lowest whole number ratio, or D, the average ratio. So first of all, if you define an empirical formulas are the lowest whole number ratio of elements to each other. So example, if you have C₂H₄, you divide the C2, so the 2 as a subscript, and 4 for the H subscript by 2, and we get the lowest ratio. So the lowest ratio would be C₄H2. And so pretty much when you're finding empirical formulas, we divide by the greatest common factor of the subscripts, and we get a least whole number ratio. And so the whole point of this is to simplify. So just think about math. When we're simplifying fractions, we just look for the GCF, and the same thing is with this thing. So we are really finding the lowest whole number ratio. And here, question 2, which of the following is not an empirical formula? So we have CH3, H2N, CH, or C₃H6. So remember my shortcut trick. If there is no subscript for some of these elements, that means it's an empirical formula. So all of these have 1 as a subscript, and the reason it works is because 1 cannot be divided by anything. So once you have except itself, but everyone knows that dividing by 1 just keeps it the same. So here we have CH3, so there's definitely a 1 here, so this is an empirical formula because it's simplest terms. Then we have H2N, 1 is definitely here, so this is also simplest. And then we have C and H, this is also simplest form. But we have C₃H6, so this is definitely not an empirical formula. But quick question, what is the empirical formula if it's C₃H6? Well, if you said C₂H₂, you are correct, because if you divide 3 and 6, the greatest common factor into 3 and 6 is 3. So 3 divided by 3 is 1, and then 6 divided by 3 is 2, so it would be 1 carbon and 2 hydrogen. And so that is it for today. So a brief overview of percent composition is how much of the whole compound is made of this element. So we pretty much divide the element's atomic mass in the compound by the total mass of the whole compound, so the whole molar mass, and then multiply by 100 and we get percent. And then with converting or getting empirical formulas is pretty much like simplifying fractions. We look for the greatest common factor and divide all the subscripts by it. And a way to convert from percent composition to empirical formulas is percent to mass to moles, divide by small times to whole. So just remember that jingle and you'll be good. And so I hope that helped you understand what empirical formulas are, how to calculate empirical formulas from percent compositions, and learning about what percent compositions really are. And so the next video is going to be converting from empirical formulas to molecular formulas. And I hope this helped you, and we'll see you later.